This is part 2 of a series on generative adversarial networks. In this video, we will implement a standard GAN model. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In the last video, we took a closer look at the loss function for GAN training. In this video, we will implement a standard GAN model using the loss function. And then we use the generator of the trained GAN model to generate two-dimensional data consisting of multiple clusters. Finally, let's look at a problem with a standard GAN called mode collapse. Before writing the code, let's first look at how the generator produces two-dimensional data as the GAN model is trained. The real data is a two-dimensional data consisting of 3 clusters as follows. Each cluster is represented by a separate Gaussian distribution. This distribution is P data, and the real data X comes from this distribution. The real data X is input into the discriminator network. Suppose that PZ is an n-dimensional Gaussian distribution as follows. The random noise Z comes from PZ. The noise Z is input into the generator network. The generator outputs G of Z. For example, the X and G of Z in the initial state is as follows. The red dots are fake data G of Z, and the blue dots are real data X. When X is input to the discriminator tries to output 1, and when G of Z is input, it tries to output 0. As the GAN model trains, the distribution of red G of Z becomes more similar to the distribution of blue X. After the model is trained successfully, the distributions of X and G of Z become similar. And the outputs of the discriminator, D of X and D of GZ, are both 0.5. That is, the generator creates fake data that looks real. The blue dots are the distribution of the real data, P data, and the red dots are the distribution of the fake data, PG, generated by the generator. X coming from PG and X coming from P data are similar. After training, we can use just the generator to generate an infinite amount of data similar to the distribution of X. Next, we will implement a GAN model that generates two-dimensional data consisting of 3 clusters. First, let's generate a dataset like the one we looked at on the previous page. This is the real data X that will be input to the discriminator. The mean of each Gaussian distribution is as follows. All standard deviations are set to 0.15. Create a discriminator model. We constructed the discriminator as a 3-layer feed-forward network as follows. The input layer receives two-dimensional real data. The number of neurons in the hidden layer is set to 64. The number of neurons in the output layer is 1. And the discriminator uses the sigmoid activation function to output a probability value between 0 and 1. Next, create a generator model. The generator is also configured as a 3-layer feed-forward network as follows. The input layer receives a 50-dimensional random noise Z. The number of neurons in the hidden layer is set to 64. The number of neurons in the output layer is 2, which is the same as the number of neurons in the input layer of the discriminator. Next, we write a class that creates a GAN model. This class takes a discriminator and a generator as input. The GAN model includes a discriminator and a generator model. This is a custom model created by subclassing Keras model. When we need to write our own training loop from scratch, we use a custom model. This allows us to take advantage of the convenient features provided by the fit function of the Keras model. For more information about Keras custom model, please refer to this site. First, let's write a function to compute the loss of the discriminator. The inputs to this function are real data x and random noise z. When z is input to the generator g, gz is output. When x is input to the discriminator d, dx is output. When the output of the generator, gz is input to the discriminator, dgz is output. We compute the loss of the discriminator using the following formula, which we looked at in the previous video. Instead of maximizing positive loss, we minimize negative loss by returning negative loss. Next, let's write a function to compute the loss of the generator. The input to this function is random noise z. Use this formula or this formula to compute the loss of the generator. We will use the first one. We define a list of metric objects for the discriminator loss and the generator loss. And we define the train step method. When you need to customize what fit function does, you should override the training step function of the model class. In the body of the train step method, we implement a regular training update. We implement algorithm 1 presented in the paper. The mini batch size is m. First, we update the discriminator k times. Sample mini batch of m noise samples z from a uniform distribution. Update the parameters of the discriminator to minimize loss d. We use the atom optimizer. Repeat this process k times. Next, we update the generator once. Update the parameters of the generator to minimize loss g. Finally, we update and return the metrics to later see how each loss changes during training. Now we create and compile the GAN model. The number of times k to update the parameters of the discriminator was set to 1, the same as that set by the authors of the paper. We write a function that observes the distribution of real data x and fake data g of z. Fit the GAN model to the real data. The mini batch size m was set to 100 and the number of iterations was set to 300. Observe the changes in d loss and g loss during training. And plot the distribution of x and g of z. The results are as follows. The blue dots are real data x, and the red dots are fake data g of z. Let's observe the changes in d-loss and g-loss during training. D-loss changes like this. This is getting closer and closer to log 4, which is 1.3863. In the last video, we saw that negative V star is represented like this. As the distributions of P data and PG become more similar, we can see that V star converges to log 4. G-loss changes like this. Next, let's verify that both D star X and D star GZ converge to 0.5. The formula for calculating d star x, as seen in the previous video, is as follows. In theory, d star x converges to 0.5. Our results also show that both d star x and d star gz converge to 0.5. Finally, let's observe how g of z changes during training. As the GAN model trains, we can see that the distribution of red g of z becomes more similar to the distribution of blue x. Let's run this code. We got the following results. This time, let's observe the changes in real data and fake data. As the GAN model trains, we can see that the distribution of red dots becomes more similar to the distribution of blue dots. Next, let's look at the mode collapse phenomenon. The phenomenon where a generator fails to produce a wide range of outputs, but instead produces only a limited set of data patterns, is called mode collapse. That is, the generator is stuck in a particular mode and cannot produce a variety of outputs that cover the full range of data. Let me give you an example. The blue dots are real data, and the red dots are fake data. At epoch 200, the generator is producing a dataset only in this region. This is the mode collapse phenomenon that occurs in a standard GAN. At epoch 400, it is producing a dataset only in this region. This is a mode hopping phenomenon. When a mode collapse occurs, the discriminator increases the second term of the loss for the data generated in that mode. The generator tries to generate data in another mode to avoid increasing the second term of the loss. This is called mode hopping. Training instability, such as mode collapse and mode hopping, is a fundamental problem faced by standard GANs. To address this problem, many variants of GAN have been developed, such as Unrolled-GAN, LS-GAN, and Wasserstein GAN. We will look at them one by one later. Now let's observe the mode collapse and mode hopping. We will generate a dataset consisting of 8 Gaussian distributions arranged in a circle like this. And we implement a standard GAN model in the same way as the previous code. Let's train this model and check the distribution of real and fake data. The results are as follows. You can see that the mode collapse and mode hopping occur as follows. Let's run this code. We got the following results. You can see mode collapse and mode hopping occurring. So far, we have created a GAN model that generates two-dimensional data and observed the mode collapse phenomenon. In the next video, we will look at DC GAN.